Okay, in this video we're going to talk about the trace of a matrix. So let's say that you have an n by n matrix A. A is an n by n matrix. So this is for square matrices. The trace of A is defined to be the sum of the diagonal entries. So for instance, let's say that A is this matrix 1, 2, 3, 4, then the trace of A, written like this, is 1 plus 4, which is 5. And okay, and if you have another example, like, something like this, then the trace of A is just 0 plus 0 plus 0, which is 0. Right, the sum of the diagonal entries. There are alternate ways of thinking of the trace of a matrix. One of them has to do with the eigenvalues. So let's say, let's just work with a 2 by 2 matrix. So let's say that A is A, B, C, D. Okay, what are the eigenvalues of A in terms of A, B, C, and D? Well, A minus lambda I is this, right? You just take away lambda from the diagonal entries, and we want the determinant of this matrix. There's a formula for this, but if you don't remember the formula, you can just compute this out. It's A minus lambda times D minus lambda minus BC, and then this is AD minus A plus D lambda plus lambda squared minus BC. So it's lambda squared minus A plus D lambda plus AD minus BC. Okay. And you see that AD minus BC, that's the determinant of A. And do you see the trace? It's right here, right? That's the trace of A. It's A plus D. So actually, you can figure out the characteristic polynomial of a matrix. The characteristic polynomial of a 2 by 2 matrix is lambda squared minus the trace of A times lambda plus the determinant of A. So for instance, let's say that A is this matrix, then its characteristic polynomial is lambda squared minus the trace, 1 plus 4 is 5, minus 5 lambda, and then plus the determinant, and the determinant is negative 2, so it's minus 2, and that's the characteristic polynomial. So you see that it's a very easy formula for 2 by 2 matrices. Okay, and what are the roots of this? Well, if you have this characteristic polynomial, right, the roots are the eigenvalues. This has the form lambda squared minus A plus D lambda plus AD minus BC. Sure, so what are the roots of this? So we can use the characteristic, what are we saying? We can use the quadratic formula, right? Because we want the characteristic polynomial to be equal to 0. So this is just an example. The roots are, okay, well the roots are negative b, and negative b being the coefficient of lambda. So it's negative negative a plus d, so it's a plus d plus or minus the square root of a plus d squared minus 4 times ad minus bc all over 2a, which is 2 times 1. And so now you see what happens is, so these are the eigenvalues, right? And we can actually express this in terms of the trace and the determinant. It's the trace of a plus or minus the square root of the trace of a squared minus 4 times the determinant of a all over 2. And so these are the eigenvalues of A. Now what happens when you add the two eigenvalues together? So lambda 1, so let's say they're lambda 1 and lambda 2, then the first one will be the trace of A over 2, plus or minus. Let's just call it the one with the plus lambda 1. So it'll be plus this thing, the trace of A squared minus 4 times the determinant of A over 2. Lambda 2 is the trace of A over 2 minus that thing all over 2. Now what happens when you add them? Lambda 1 plus lambda 2, you get, see, these things will cancel when you add them. And then what you're left is half the trace of A plus half the trace of A. That just makes the trace of A. So we've just discovered that for 2 by 2 matrices, we've just proven that for 2 by 2 matrices, the trace of A is not just the sum of the diagonal entries, it's not just A plus D, but it's also the sum of the two possibly complex eigenvalues of the matrix. And in fact, this is in general, okay, we haven't proven this, but it's a general fact that for an n by n matrix with complex entries, the trace of A is the sum of the eigenvalues of A. Possibly repeated, right? Counting, counting multiplicity, right? I mean, whenever we're talking about sums of eigenvalues or products of eigenvalues, it's counting multiplicity. So for instance, if you have this matrix A, which is 2, 0, 0, 2, or okay, let's make it maybe not 2, 0, 0. Just to take a simple example, let's say it was 5, 0, 0, 5, then the trace of A is 10, and the eigenvalues, well, there's one distinct eigenvalue, which is 5, but if you count them separately, right, it's 5 with the multiplicity of 2, and then when you add lambda 1 and lambda 2, you get 10. So lambda 1 can be equal to lambda 2. Right. Okay. So we've seen some interesting facts about the trace. It's the sum of the eigenvalues, and it's the sum of the diagonal entries. They're both equivalent. And one property of the trace is that if A and B are n by n matrices, then the trace of A times B is equal to the trace of B times A. So one way to think about this is if you have two matrices A and B, and then you multiply them in either order, when you add the diagonal entries, you get the same thing. Another way of thinking about it is if you take the eigenvalues of A times B and the eigenvalues of B times A and add them, you get the same thing. Let's prove this in the case when n is 2. And when n is arbitrary, it's just more complicated. So I would encourage you to either try to come up with the proof on your own or look it up in the book. But in the case of n equals 2, okay, let's say that A is A11, A12, A21, A22, and B is B11, B12, B21, B22. Then if you do A times B, you can actually just say what the entries are, right? It's A11, B11 plus A12, B21. And then A11, B12 plus A12, B22. And then A21. It doesn't even matter because we're taking the trace. We're just looking at the diagonal entries. So let's just skip to the last one. A21, B12 plus A22, B22. And then it's, something. Okay, and what's BA? So let's write it again. Okay, let's figure out the diagonal entries. So it's B11A. Well, let's write it in the order where A comes first. So it's A11, B11 plus A21, B12. And then it's something, and it's something, and then the last one is A12, B21 plus A22, B22. And so the trace of AB is this plus that. And the trace of BA is this plus that. Now, do you get the same thing? Yes, right? Because this term matches with that term matches with that term matches with that term, and that term matches with that term. So therefore, we can actually just see that the trace of A times B is in fact equal to the trace of B times A. Okay. And again, the same proof holds for general n. It's just that there are going to be a lot more terms being added together. And it's a good idea to read a proof to see how it's done. Okay, so let's just take it for granted that the trace of AB equals the trace of BA. Well, one consequence of this is that if you have a matrix B, which is P times A times P inverse, for some invertible matrix P, then the trace of B equals the trace of A. I'll give one argument. There's another argument, but I'll give one argument thinking of the trace as the sum of the diagonal entries. Okay, so we want to look at the trace of PA, P inverse, and you want to show that it's equal to the trace of A. Let's see here. How do we do this? Oh, well, the trace, so the trace of PA P inverse is equal to the trace of PA times the trace of P inverse using the property that we had before, right? We take this to be one matrix and that to be our other matrix, and it's oh no, sorry, this is not what I want to do. We're applying the theorem, and the theorem says that you can switch the order, so it's the trace of P inverse PA. There we go. It's the trace of P inverse times PA. Okay, because we're just switching the order of these two matrices. And then P inverse times P is just obviously the identity, and then the identity times A is this, the trace of A. So it's the trace of A. There we go. That's the proof. So here we're using by the previous proposition. So that's the first argument. And then the second argument is using the fact that the trace is the sum of the eigenvalues. And we can use the fact that B and A have the same eigenvalues. All right, that's a theorem about two matrices that are related in this form. They have the same eigenvalues, and therefore the sum of the eigenvalues must be the same. So the sum of the eigenvalues of B must be equal to the sum of the eigenvalues of A. And here we're using the fact that when you have n by n matrices, so these are n by n matrices. Maybe I should have said that. When you have n by n matrices, where is it? We're using this fact that you can think of the trace as, in terms of the eigenvalues, as the sum of the eigenvalues. Okay, and by the way, matrices that are related in this way are called similar matrices. So we say that A is similar to B. So similar matrices have the same trace, and they also have the same determinant, right? And that's one way to tell if you have two matrices, are they similar? If they have different determinants, if they have different traces, then they're not similar. Okay, thanks for watching.